all of us. And our next talk by Sofia Belikovetsky is about another subject that is going to take more and more significance in our lives, and that is the relationship between virtualization environments and the underlying hardware. And the title of her talk is The Butterfly Effect, Actively Manipulating VMs Through Hypervisor Introspection. Yeah, this. So a round of applause, first of all. And the traditional.
Cheers! Welcome to B-Sides, Sophie. Let's all have fun with the butterfly effect. Please take your seats.
You.
Sophie, the stage is yours.
Thank you. Hi. So like mentioned, I'm Sophie. And this talk is titled The Butterfly Effect. After a term in the chaos theory that says that even minor changes in the right time can cause big consequences. And the example that's usually given is that even a butterfly flapping its wings on one side of the world in the right time can cause a storm on the other side of the world. So it's very similar to what we're going to show, how by manipulating single values in the memory of the hypervisor itself, we can Okay. So how by manipulating values in the hypervisor itself, in the memory of the hypervisor, we can lead to big results in the virtual machines, such as even stopping cyber attacks. So a bit about myself. It's a really big photo. So I have over 10 years of experience in the cyber security and cyber intelligence space. And currently, I'm in the final stage of finishing my PhD in the Ben-Gurion University in Israel. And today, I'm going to talk about a challenge that we had in one of our recent projects. So we had in our lab, we had a huge private cloud environment. And most of the virtual machines running on this environment were fully under our control. But some of the virtual machines were provided by external vendors and were meant to function as a black box, at least from the security point of view. An example of such a VM is a virtual router that was meant to be placed as is in our environment, of course configured correctly, and just to run. We can't really connect to it directly. We can't force the vendor to install any of our security agents inside. And practically, we're blind to what's really going on inside the virtual machine. And this problem is actually very popular. Of course, it's the same thing in public cloud infrastructures, where, let's say, Amazon is providing the infrastructure and the environment, but the virtual machines that we are using, they are not connecting to them directly. They're not forcing us to install anything inside. And what they're doing right now in order to see what's going on is practically only monitoring the network communication, looking what's going on, what's going into the machine and what's going on from the machine, and trying to find network anomalies. And that's what's going on, and this was what we did in our network. But we wanted to challenge ourselves. We decided this is not enough. And we wanted to find a solution under the following limitations. So one, we cannot connect to the virtual machine. Okay. Okay. And the second thing that we can't install any agent inside. And the third thing that we do not want to rely only on the network communication, on the external network communication. So we started reading about it, and pretty right away we came to this really big body of work, of research around how to understand what's going on inside your virtual machine from the outside, only from monitoring the network, the memory. And the basic idea behind this body of work is do not try to secure your virtual machines the same way you try to secure your physical workstations. Here you have an additional layer, the layer of virtualization, and let's take advantage of this layer to enhance our security. And so this talk is about that, is about our thinking process and how we took advantage of this ability, how we built the security strategy of both identifying the threats, the security threats inside our virtual machines, and remediating them from the outside. Okay, so let's talk about this virtualization layer. So the main component of the virtualization layer is the hypervisor, and we have two types of hypervisors. The first type is a native hypervisor or bare metal, which runs directly on the hardware. The hypervisor's job is to manage and to stop and run the virtual machines that are running on top of it. So this is a popular architecture where the hypervisor is running on top of the hardware. And an example of such hypervisors is ES6 and Hyper-V. This is usually more expensive. And the second architecture is the hosted hypervisor, which is running as an application on top of the existing operating system. It runs the virtual machines on top of it. And this is usually a cheaper setup. And this was a setup in our private cloud environment. And the hypervisors that we used is the KVM. So when looking at this architecture, security research found that straight away that there is something interesting in the memory. Just because the virtual machines are running on top of the hypervisor, the memory of the virtual machine resides within the memory space of the hypervisor, meaning that by correctly parsing this memory, we can understand what's going on inside each of the virtual machines. And this is exactly what we wanted. So what are we going to do with this ability? Okay, so what we're going to do with this ability? So first of all, we started thinking, okay, this is great. This is exactly what we want. We want to see what's going on inside the virtual machines. Maybe someone already did it. Okay, maybe we don't need to do the hard work. So we looked for commercial tools that are actually doing hypervisor introspection. And the only thing that we found was the Bitdefender tool, but it focuses only on, or mainly on ES6. And of course, we have the KVM hypervisor, and it's not suitable for that. So this means we need to do it ourselves. Then we looked at the research. Okay, what are the researchers doing? So a lot of the work is focused on monitoring the memory in order to find security threats. Okay, this is very interesting, but we wanted to start with something simple. So because all the virtual machines that are running in our environment that we want to monitor, that are really interesting and we don't have any access to, are provided by vendors, they also are pretty much predictable. That there are services that are running and we know what is actually going on inside, or we can guess. So the first thing that we wanted to implement was a whitelisting of running processes. We will have some pre-prepared list of what should run, and we will monitor every new process and see if it matches this list. So let's talk about how it's actually done. So if I could write an agent, this will be pretty much the logic behind this agent. I would just go through all the running processes. I would find out the information that is relevant that I want to, that identifies this process, and I will check it against a predefined list. But by looking only on the memory, I have this huge blob of memory, and I'm losing all the capabilities that the operating system is providing for me. So what I'm losing just by looking at this blob, not by running inside the operating system, is, of course, I can't run any of the APIs of the operating system. I cannot rely on any security events or operating system events. And the most important thing that I used to really appreciate is the translation of physical and virtual addresses. As you recall, the addresses in memory are virtual, and I really need the physical address in order to get the data. So what am I missing? What do I need to know in order to implement this? So we started working on a Linux, Linux operating system. And in Linux, the running processes is a circular double linked list of task structures. And every data structure has the information that I need in order to identify a process. And the beginning of this list is a kernel symbol that's called any task. So I need several things in order to do this. First of all, I need to know what is the virtual address of any task. Then I know I need to translate it to the physical address to know where in this huge blob of memory is the actual beginning of any task. Then I need to take every task and cast it into the right task structure according to the right Linux version, of course, and retrieve the information that I need to find the next task, the virtual address of next task, and do this whole process all over again. So thank God I didn't have to do it by myself. Of course, there is a tool. It's been here for a while, so maybe most of you already familiar with it. So there's a tool, libvmi, in GitHub. It's a C library that runs on the hosts, and it queries the hypervisor. And its main job is to translate between the physical and the virtual addresses of each virtual machine. And right now it supports KVN and Zen hypervisors, but it's in development still, and it supports multiple guest operating systems. So this is exactly what I wanted, and we've used this library. And the thing that we need to provide to this library in order for it to work is two things. So first of all, we need to provide some kind of a mapping between kernel symbols that we rely on and their virtual address. And there are two ways to do this. There's like the easy way and the hard way, of course. And the easy way is a bit of cheating. So either you have to run like a script once on this virtual machine to get this mapping, or you can ask the vendor. Of course, you can do both, so easy way is not really an option. And the hard way is to look at the memory and heuristically find the process list, and then to find the beginning of the init task. And this is what we did, of course. And the second thing that you need to do is provide the right header files for the kernel structures for the specific virtual machine that you are running on. But if you're going to do it the easy way, just so you know, you can just take the system map file from your computer, from the inside the virtual machine, which is just a mapping of kernel symbols and their virtual addresses, and just supply it to the libvmi. And the way libvmi works is it receives all the kernel symbol mappings, it takes the right virtual addresses, it travels the page table and the page directory, it retrieves the right page that is needed, it gives it back to the application. The application takes this big blob of memory, casts it to the right structure that we have provided before, takes the information that it needed, and moves on. And the way it looks, it's It's really like a textbook example of libVMI. This is from within the virtual machine. It's running a PS after SSH in inside. And you can see that we get all the information about the process. We have this like demo malware process running inside. And this is what we're getting from the outside without supplying any password of the virtual machine. Just by monitoring the memory of the hypervisor, we get the same information. We, of course, get the process ID and the process name. So this is very cool because you can get all the information you want from the outside. So what we did for our first security application was we defined something that we called process identity, and those were the parameters that we have used for now. So we have defined that every running process is a subset of its name, it's the file on disk that is running from, the shared object that are loaded inside this running process, the permission of the process, and the user that is connected. And we have monitored our environment for several weeks. We found out, we built some kind of a baseline to see what's really going inside and if it should run. And once we have looked our baseline, we have compared every running process against this baseline. Okay, so this was our first security application. And it worked pretty well, and then we decided to move to something more complicated. So while we were digging inside our kernel structures, in order to get the shared object, of course, we started with task struct that has like a list of files, that is an array of files that is connected to it. And a file can be several things. I should really use the clicker. Can be several things. And one of the things it can be is a socket. And we found it really interesting. So by digging inside, I note that are a socket type. 2 layers down, there is a sock struct, which contains information about the network connections that are related to this process. And the information that we have in this task is source IP, dest IP, source port, dest port. So what can we do with this information? So we started thinking about, right now, the first application only focused on the virtual machine itself as a separate unit. But we are controlling all the data center, and we can see all the virtual machines. So by seeing all the virtual machines, we can do bigger things. So we decided to create a context-aware firewall. So we already had firewalls in our network, but we had several problems with them. First of all, we don't have a firewall between every virtual machine, of course. They're usually on the edges of the network. The second thing, from the outside, they're very limited. We can only see the network information. And third, if we would have been able to put an agent inside, we could have combined the network information with the information, with the internal state of the virtual machine in order to create smart rules. So this is exactly what we did using the hypervisor introspection. So we have combined our process identity with the network communication information in order to create smart firewall rules. So what are like an example of a rule that we can create? So we can create the following rule. We can make sure that only an application that is running from a specific place in memory that is on disk, that is, it has only specific DLLs that are loaded inside with a specific user with specific connections, can talk to a specific process identity on the other side of a data center. And that's why we are creating like a context-aware firewall. And the way it looks is this. You can see from running, let's start from inside, we get the information about the connection itself. And of course, we know what is the process ID that is running it. And this is what we get from the outside. It's not like, we didn't construct a GUI, just a bash. So we can see that from the outside, we can match the network communication to the process that is running it, to the client process in this case, and of course we can look at any other information that is relevant in order to construct this firewall. Okay, great. Okay, so now what? We did it. It worked great. We found out a lot of security threats, but what we can do with it? So we were thinking about it. So far, we just looked at the reading capability, but there is also a way to write the capability, write into memory. So the thing that we were thinking about was, what if we write into memory? Can we manipulate the behavior of the virtual machine? Probably, right? We can always do some kind of damage if we write into memory. Okay, then we said, if we write into memory, can we create a specific outcome, a certain outcome? Can we, for example, stop a process? Maybe, okay, this is interesting. Maybe we can do it. So let's look into that. The first thing we wanted to do was exactly this. We have already a whitelisting application. Can we stop a process or terminate it once it does not match our baseline? And how we did it was just, we said, okay, let's look at the task track that we already have and try to find some suspicious elements that can influence the behavior of the virtual machine. So just by looking on the struct, we have several leads. Okay, the first one is literally almost always the first, is the state with really interesting comment. There are a lot of others, like flags. Maybe if we change the flags, we can stop the process from running. Maybe if we play with its scheduling and the CPU time, priority, and also exit states. Okay. So we decided to go out with the first, which was the easiest, and try to see what are the values that we can put inside. And if you can read it, like everything here looks interesting. Probably everything you will try will do some kind of damage to this process. But we wanted to have a specific outcome. So So in order to get a specific outcome, we started to read about what really every value means. And pretty straight away, we got into the task interruptible, which means that we can change the value, that even if there is a signal that signals it to wake up, it will not wake up until we wake it up manually. So this is exactly what we tried. We have took our demo malware process that was running that we wanted to terminate. We have assigned the task uninterruptible value into the state offset of the task track. And so what happened? And what happened was exactly what we wanted. The state of this struct went to uninterruptible, which means that if we want, we can run it again. And right now, when the process is frozen, we can actually take its memory. We can retrieve its memory and code data and analyze it. And if we want, we can even resume its running without hurting any other of the running processes inside the same virtual machine. And so it was nice, but the thing that we wanted to do after that was to kill it entirely, to make it to turn it into a state that it cannot be resumed. So this is what we did. We played with the exit state as well of the task state and the exit state as well. And the thing we found interesting was the exit dead. And my time is up, so I will just go through it briefly. We have assigned both values, and we, of course, got to where we wanted. Okay. So I will not go through all those slides. Yeah, a couple of minutes? Okay. Okay, great. Okay, because I have a lot more to say, but never mind. Okay, so this looks a bit random, but it wasn't really random. It was by reading the open source code, of course, and looking at the manuals. And by reading the code and trying to figure out how to get to a state that I want to get to. This is not necessary. There is code, there is any path in the code that goes into this state. It's imagine like a state machine that usually the code goes into certain positions, but by manipulating the memory, I can take my running position and place it everywhere that I want inside this state machine. So by manipulating both those memories, we achieved the dead should never be seen state, of course, because it should never really happen. And okay, so this is what we did for the running processes application. And the second application that we wanted to create was an active firewall. We already have our context-aware firewall, and the thing that we wanted to do is exactly the same thing. We have a process running, and we want to kill it. We did the same way of thinking. We found some suspicious places, suspicious values that we can change. We changed them according to the correct value after reading, of course, the manuals and the code. Some examples of how it works is, for example, here we can see that if the SOC dead flag is raised, then it will not process the data. Another example is if the SOC done flag is turned on, then it will not go, it will not bring the memory further, it will break. And those are exactly the way of thinking that we have applied to this project. And this is not everything that is needed to stop a project, but this is the way of thinking is the same. So we have changed the state of the flags, put it inside, and what happened is not really exciting from like the visual point of view, but it's very exciting when it's really happening. The process, we killed the process from the outside. So here we have a process running inside, two virtual machines are communicating with each other, and by changing minor values in the hypervisor, not touching the virtual machine at all, we have, of course, terminated this process, this communication. And the cool thing is that the operating system is doing the hard work for us. We have changed the values, and the operating system understands that it is in the state that it needs to close this connection, and it frees all the resources that were used for this network communication, and leaves the state clear. Okay, so why this is cool? We have done what we set up to do. We have built a no agent, no touch, not only relying on network communication solution. This is really cool also because any malware that is running inside, it will be a bit harder to evade because we are seeing all the memory. And the attacker doesn't really know what we are monitoring for, what in memory we are looking at and where. And the operating system does all the work for us. Once we are once we are moving from one state to another state, the operating system knows how to do the job and close all the things that it needs to close. And the cool part here is by some more effort, especially in KVM, because we don't have events, we can also run code. So this will be probably for next talk, not now. Some caveats, things that are said that are not true or not really are problematic. So one of the problems of a hypervisor introspection is posing the virtual machine. Every time you do, you need to translate a virtual address and a physical address. You need to pose the virtual machine in the current implementation. So what we did in order to overcome this, we have worked with some heuristic access. We are always monitoring the network and trying to find heuristically if the information is fresh or not, if it's relevant or not. So this is one thing that we did in order to overcome this. The second thing is the mapping between the kernel symbols and their virtual address. So if a KSLR is turned on, then what I said before is not really relevant. A system map will not be relevant after every reboot. So in order to overcome this, you need to do the heuristic method every time. You need to every time to scan the memory, every time the system comes up, and find the right kernel symbol locations. And I will not talk about the last one. If you want, see me after. So some takeaways. So this was a big challenge, and I think that the limitations, even though they were really strict, really helped the solution. And I do believe in limitation based on innovation. This is a really cool platform. You can get almost anything from the memory of the virtual machine. So the possibilities are really endless of what you can do with it, and it's not really utilized enough right now. And of course, you can always do harm, and I learned it the hard way. So use it with caution. Thank you.